Hi, I'm Chris with Sanderson Test Prep, and in this video we're going to go over 3 sample questions that a student recently sent over to me for some calculus help integrating by using U substitution. So let's jump into our first example. So here we see the integral from -1 to 2 of x over x squared minus 5. And the way that we know that this might be a candidate for U substitution is by recognizing that if you have a difference of 2 parts of an expression by an exponent of 1, so here we have x squared and x to the first. So if the exponents differ by 1, then oftentimes that's an indicator that U substitution might be involved, because when you set a value for U and then take the derivative using power rule, you'll oftentimes be able to cancel out a portion of your expression. And that's the whole purpose of U substitution. So let's see how that would work here. So for U substitution, what we're going to do first is set a value for U, and it's going to be equal to usually the most complex portion of the expression that you're trying to integrate. And in this case, where we have that difference in the exponents, they're off by 1, then you're going to set your U expression equal to the expression that has the larger exponent, so that when you take the derivative, you'll have the derivative in terms of the other exponent. So in this case, we're going to set U equal to x squared minus 5. And now let's walk through how U substitution works. You set a value for U, and then you find the derivative. So here, du, whoops. So let me zoom in a little bit on this. So du dx would be equal to 2x. And then if we rearrange a little bit, what we want to do is we want to get dx by itself so that we can substitute into the integral. So here, du would equal, not writing very pretty U's today, but du will equal 2x dx. And then dx will equal du over 2x. So once you have your value for U, and then you solve for du, and then put it in terms of dx, so that you can substitute it back in. So all those highlighted pieces together are going to come together when we actually plug back in the substitution part of this process. So the integral from -1 to 2 of x over our value for U, which is the x squared minus 5, and then times dx. So in place of dx, we're substituting in du over 2x. And voila, that's the purpose of U substitution, is that we're able to simplify the integral quite significantly. And so here, when we pull the 1/2 out front, what we end up with is the integral of 1 over U du from -1 to 2. And now we can actually integrate. And so here we would have 1/2 times the natural log of the absolute value of U. And we're going to substitute back in terms of x. So we'll have 1/2 times the natural log of, so we know that U was x squared minus 5. We're integrating from -1 to 2. And now we can go ahead and plug in those values. So this will equal 1/2 times the natural log of the absolute value of 1, which is just going to be 1. So I'll just write that as natural log 1. And then minus 1/2 times the natural log of the absolute value of 4, which will be natural log 4. And here, natural log of 1 is equal to 0. So this simplifies to just -1/2 ln 4. So that's our first example of U substitution. And the key parts are making sure that we are comfortable setting the value for U, taking its derivative, and then plugging in for dx. So that's the process that we're going to use whenever we use U substitution. Let's see a couple more examples of different ways that this can be applied. So here we'll look at another sample problem. And so first things first, if we look at this one looks a little bit different because we don't have exponents that differ by 1. So it doesn't have that traditional indicator of U substitution here. But let's see how this one might work, because oftentimes when you have roots the expression inside the root is going to be your value of u. And let's see how that'll work out on this indefinite integral. So if we set u equal to the expression inside the root, that means u would equal 3 minus x. And so what's our next step? So hopefully you said we're going to take that derivative, and that is what we do. So we have du dx is equal to negative 1. And when we rearrange and solve, we're going to get dx is equal to negative du. And let's go ahead and plug in those values and see how it works. So here we have x times, and this will be u to the 1/2, or the square root of u, and then times negative du. And we can pull out the negative, and so we have a negative integral of x times u to the 1/2 du. All right, so this one looks a little different because that x didn't cancel out with anything, and we can't integrate in terms of du if we have an x in there. So let's see if there's a way for us to get everything in terms of u. And there is. So remember, when you use U substitution, so that u expression doesn't disappear, and when you have a remaining x but you need it in terms of u, you can rearrange your u expression and substitute in place of x. So x here would equal 3 minus u when we rearrange this. And if we plug that in for x, then we'll have everything in terms of u. So this will be, zoom in a little bit here, oops, too much. So this will be the integral of 3 minus u times u to the 1/2 du. And now we can distribute inside those parentheses. So this will be the negative integral of, once we distribute that, it'll be 3u to the 1/2 minus u to the 3/2 du. And then from here we can integrate. So when we integrate this, we'll have negative 1 times, so this integral will be 3u to the 3/2 times 2/3. And I'll write it out and then simplify afterwards. But we add 1 to the exponent. And then when you divide by 3/2, that's the same thing as multiplying by 2/3. So this will be times, maybe I'll just erase this and sneak it in over here, times 2/3. And we'll see that those are going to cancel out. And then minus u to the 5/2. And then divided by 5/2 would be times 2/5. So that's our integral. And now we can distribute our negative, cancel terms out, and clean this up a little bit. So we'll have negative 2u to the 3/2, and we might as well go ahead and plug in our original u value back in. So if we look up here, we had u equals 3 minus x, and if we plug that in here, so we'll have negative 2 times 3 minus x to the 3/2, and then plus 2 times 3 minus x to the 5/2 over 5. And because it's an indefinite integral, we have to add our constant at the end. So this will be the final form of our indefinite integral for x times square root of 3 minus x using U substitution. Let's try one more problem to make sure we've got it down. So here we see the integral of sine of root x over root x. So for this, let's take a guess what we think we're going to do for our value of u. So hopefully, if we're getting the hang of it a little bit, we recognize that we want u to be root x in this case. And for du, so it's a good habit to get into if you're going to have to derive or integrate, to get used to writing out your roots in fraction exponent form. So here, our du dx value will be 1/2 times x to the negative 1/2. And if we do some rearranging here, so we'll have du equals 1 over 2 root x dx, and that means dx will be 2 root x du. All right, so now that we've done that part, let's go ahead and plug everything back in. So that'll give us the integral of sine u over root x, and then times 2 root x du. And I'm just going to move this over a tiny bit. It's a little crammed in here. So let's slide that to the right. And here, our root x's will cancel out. We can pull the 2 out front. And this integral is going to look a lot cleaner for us. So here we have the integral of sine u du. And so what's the integral of sine? It's going to be negative cosine. So we'll have 2 times negative cosine u. And when we plug back in our u expression, it's going to be 2 times the negative cosine of root x plus c. And we'll probably see this written out in final form with the negative out front of the coefficient. So negative 2 cosine root x plus c is the final form of our indefinite integral of sine root x over root x dx. So those are 3 examples of different ways that we'll see the application of U substitution. If you have questions or want to learn more, please check out our other videos, and thanks for watching.